Welcome to the Deep Dive. Today, we're going straight into the heart of a system that quietly powers so much of the internet, the Google File System, or GFS.
That's right. We're digging into the original 2003 research paper from the Google engineers who actually built it.
And for you, someone who needs to quickly get a solid understanding of important technologies, well, this is your shortcut.
Yeah, we've basically distilled the core of this foundational work. The goal is to give you the essential knowledge without you having to spend hours reading the paper itself.
Exactly. Our mission today is to unpack the surprisingly simple yet incredibly effective principles that made GFS work so well for Google's massive data needs.
We want to understand the core problems they faced and, the clever solutions they came up with.
And the fundamental challenge was huge, wasn't it?
Oh, absolutely. It was essentially, how do you build a file system that can handle enormous amounts of data spread across thousands of, well, everyday computers?
And make it fast, reliable, and serve countless users all at the same time.
That's the crux of it.
Okay, let's unpack this, starting with a really pivotal idea. How GFS looked at hardware failures. It wasn't a case of expecting everything to work perfectly all the time, was it?
Not at all, no. Traditional file systems, they often assumed that your servers and hard drives would mostly be reliable. Pretty safe bet for smaller scales.
But Google wasn't operating at a small scale.
Definitely not. They were operating at a scale with hundreds or even thousands of machines, all built from standard, less expensive commodity parts. They knew things would go wrong and often.
Right. We're talking about everything from software glitches, OS bugs, human errors.
And the inevitable hardware failures,
Yeah.
disks, memory, network issues, power outages, you name it.
It was just a given, not some rare exception.
Precisely. And this fundamental shift in perspective that failures are just a normal part of life at this scale, it really shaped the entire design of GFS.
So things like constant monitoring.
Constant monitoring, error detection, built-in ways to keep working when things fail, that's fault tolerance and automatic systems to recover from errors.
They weren't just bolted on at the end.
No, they were absolutely fundamental to how GFS operated right from the start.
Okay, here's where it gets really interesting. Because dealing with constant failures wasn't their only big challenge, right? The sheer size of the files they had to manage was also a game changer.
Absolutely. You have to forget about files measured in kilobytes. GFS was designed for a world where multi-gigabyte files were common.
Gigabytes.
Yeah, often containing massive collections of data like all the web documents Google was indexing. Trying to manage billions of tiny files just wouldn't cut it at that scale.
So this meant they had to rethink some pretty basic assumptions about how file systems work, like how they read and write data and the size of the storage units they use.
Exactly. The sheer volume of data directly influenced these fundamental design parameters. And then there was another key observation about how this massive data was typically being used.
It wasn't constant editing and rewriting like you might do with a document.
No. Their analysis showed that the vast majority of changes actually involved adding new information to the end of files. Think of massive logs or continuously growing data sets, archival data.
Or even intermediate results from big data processing jobs.
Exactly. Overwriting data or making random changes in the middle of a file. Relatively rare in their main use cases.
So what's fascinating here is how this dominant pattern, just appending data, became a central focus for optimization.
Right. Making GFS fast and ensuring that these appends happened reliably, even when multiple computers were writing at the same time, was key.
And that had implications for caching, didn't it?
It did. It meant that a common speed boosting technique in other file systems, keeping copies of frequently used data close to the applications, what we call client-side data block caching it, became less effective.
Because if you're mostly just adding to the end, the data you might need next is probably new.
Exactly. New data, not something you already had stored locally, so the cache hit rate wouldn't be that great for that workload.
Right. Makes sense.
And this deep understanding of their specific needs led to another key innovation. They weren't afraid to design the file system hand in glove with the applications that would be using it.
So they could actually tweak the file system itself to better fit how their internal tools worked, rather than forcing their tools to fit a generic file system model.
Exactly. A prime example is GFS's consistency model. They deliberately made it a bit more relaxed than some traditional file systems.
Relaxed consistency. That sounds risky.
Well, it sounds risky, but it made GFS simpler to build and run without causing major headaches for their specific applications, which were built with this in mind.
Okay.
And they also introduced a special operation called atomic record append. This allowed many different computers to add data to the same file concurrently, without needing complex external synchronization between them.
We'll definitely need to dive into that append operation more. Okay, so we've got the core assumptions. Failures are normal, files are huge, writes are mostly appends, and they could customize the system for their needs. Now, how do they actually put this all together? What were the main parts of GFS?
So, the architecture of GFS centers around three main players: a single master server, multiple chunk servers, and multiple clients.
Okay.
Think of it like a conductor that's the master leading an orchestra, the chunk servers, for an audience, the clients.
A single master. With potentially thousands of chunk servers and clients, that sounds like it could become a major bottleneck.
Yeah, it might seem counterintuitive at first glance, but we'll explain how they cleverly avoided that. For now, just understand that the master is the brain of the operation. It manages all the metadata.
Metadata meaning information about the files.
Exactly. Information about the files and their locations. So the directory structure, who has permission to access what, and crucially, which chunks of data make up a file and where those chunks are stored across the chunk servers.
Got it. And the chunk servers are the ones that actually hold the data.
Exactly. Files are broken down into fixed-size pieces called chunks, typically 64 megabytes each in GFS.
64 megabytes, that's pretty big for a block size.
It is, and we'll talk about why. Each chunk gets a unique 64-bit ID from the master. The chunk servers are responsible for storing these chunks on their local hard drives, just as standard Linux files.
And for that all-important reliability, they're not stored just once, right?
No way. Each chunk isn't stored just once, it's replicated, usually 3 times, across different chunk servers, preferably on different racks.
Redundancy is key for surviving failures. And the clients are just the applications that need to read and write these files, like map-reduce jobs, for instance.
Yes, when an application wants to use GFS, it uses special client library code that understands how to talk to the GFS system. This client software first talks to the master primarily to figure out where the data it needs is located, which chunk servers have the chunks for the file it wants. But then, once it knows which chunk servers hold the data, the client talks directly to those chunk servers to perform the actual reading or writing.
So the master is only involved in the metadata operations, like the initial lookup, not in the heavy lifting of the ongoing data transfer.
Precisely. That makes a lot of sense for preventing that master bottleneck we were worried about.
It does.
And it's worth noting here that GFS wasn't trying to be, a general-purpose file system that could work with any existing application out of the box.
They weren't aiming for POSIX compliance.
Exactly. They made a conscious decision not to fully implement the standard PO6 API. This gave them the flexibility to optimize GFS specifically for their large-scale distributed environment, rather than trying to fit into a general-purpose mold, which often involves compromises. They didn't need to hook into the Linux VFS layer.
Interesting trade-off. And you mentioned earlier that neither the client applications nor the chunk servers keep their own separate caches of the file data itself. Why was that?
Right. For the clients, remember, they were often dealing with such large files and streaming data, or working with massive data sets where they read through the data once. Keeping a local copy of the data wouldn't necessarily give them a big speed boost in those scenarios.
And it would add complexity.
Huge complexity. You'd have cache coherence issues. Not having to worry about keeping these local data caches up to date simplified the client software considerably. Clients do cache metadata, though.
Oh, okay. And the chunk servers.
As for the chunk servers, well, since they were already storing the data chunks as regular files on their underlying Linux operating system, they essentially relied on the operating system's built-in file system cache, the Linux buffer cache, to keep frequently accessed data in memory.
So no need to reinvent the wheel with another layer of caching on top of what the OS already provided.
Exactly. Leverage the OS.
Okay, let's circle back to that single master design. You said it helped avoid bottlenecks, but what were the actual advantages of having just one central point of control, and how did they really prevent it from being overwhelmed?
Well, having a single master really simplified the design in many ways. It allowed for consistent and coordinated decision-making across the entire file system. Things like deciding where to create new chunks, how to manage replicas, coordinating snapshots.
The master has the global view.
Precisely. Because the master had a complete up-to-date view of the system's state, or at least very nearly up-to-date, it could make smarter, globally optimized choices.
But still, the risk of that single master becoming overloaded or, worse, failing, that seems like a single point of failure.
It's a valid concern. They minimized the load on the master, as we said, by ensuring it wasn't involved in the actual transfer of data. Clients talk directly to chunk servers for reads and writes.
Right, the metadata versus data path separation.
Exactly. When a client wants to read a file, it asks the master just once, where are the chunks for this file range? The master replies with the chunk locations. The client then caches this information for a limited time.
And communicates directly with one of those chunk servers to get the data. It doesn't need to ping the master for every single read operation on the same chunk.
Correct. It's like asking for directions once and then driving straight to your destination repeatedly without needing to ask the operator again every block.
Nice analogy.
And to make things even more efficient, the master often proactively sends the client information about the locations of the next few chunks it's likely to need, especially for sequential reads, kind of anticipating its future requests.
Clever optimization. Now let's talk about the size of those data chunks, 64 megabytes. You mentioned it's much larger than typical file system block sizes, which are often in the kilobytes. What was the thinking behind such a large size?
Yeah, 64 millibytes definitely chunky. It was a deliberate design choice that brought several key advantages, especially for their workload.
Okay, like what?
First, it dramatically reduced the amount of communication needed between clients and the master. Think about it. For the large sequential reads and writes that were typical in their environment, a single request to the master for chunk locations could cover a huge amount of data, that full 64 millibeats.
So fewer requests means less load on the master.
Exactly. Less back and forth with the central authority is crucial for handling scale. Second, because clients would often be working with the same large chunk for an extended period, they could maintain persistent network connections, TCT connections, to the relevant chunk servers for longer.
Which reduces the overhead of constantly setting up and paring down connections.
Precisely. Connection setup isn't free. Third, and this is really important, it helped keep the amount of metadata the master had to manage relatively small.
How so?
Well, it's much more efficient for the master to keep track of, say, 1,064 millibeat chunks than, 16 billion 4KB blocks for the same amount of data. This smaller metadata footprint made it feasible for the master to keep all of that crucial mapping information in its fast RAM.
Which is key for performance. We'll come back to that metadata management. But were there any downsides to having such a large chunks? It seems like if you have lots of small files, maybe just a few kilobytes each, you might end up with a lot of wasted space within that 64 millibyte chunk, right? Internal fragmentation.
That's a valid concern. GFS did use a technique called lazy space allocation, meaning physical disk space for a chunk wasn't allocated until data was actually written to that part of the chunk. So it wasn't quite as bad as allocating the full 64 millibeat up front.
Okay.
But yes, for small files that only use a fraction of a chunk, it could still lead to a potential issue if many clients try to access the same small single chunk file at the same time.
Ah, the hotspot problem.
Exactly. The few chunk servers holding that popular chunk could become overloaded. Think of maybe a common executable file everyone needs to run simultaneously as part of a batch job.
And did that actually become a problem in practice?
It did arise in some situations, yeah. For example, with their system for running batch jobs. When a single small executable file needed to be launched on hundreds of machines at once, the handful of chunk servers storing that file could definitely get hammered.
So how did they mitigate that?
Their solutions involved increasing the number of replicas for such frequently accessed small files, maybe more than the standard 3. They also tried staggering the times when applications started, so not everyone hit the file at the exact same microsecond.
Spread the load out over time.
Right. They even considered allowing clients to perhaps read the data directly from other clients that already had it in a sort of peer-to-peer fashion for those specific hot files, though the paper doesn't say if they fully implemented that.
Interesting. So they had to adapt and find solutions as they encountered these real-world challenges. Now, you mentioned that the master keeps all its metadata in memory. What kind of information are we talking about precisely, and why was keeping it in RAM so important?
Okay, so the master primarily manages 3 critical types of metadata. First, the file and chunk namespaces. It's essentially the directory tree structure of the file names. Second, the mapping of each file to the individual 64 millibeat chunks that make it up. And third, the current locations and all the copies, the replicas, of each chunk across all the chunk servers.
And keeping all of this in the master's fast random access memory, the RAM,
Provided a significant speed advantage for any operation that needed to look up or modify this metadata. which is, almost everything the master does. It also enabled the master to efficiently perform regular background scans of the entire system state.
And these background scans were essential for things like garbage collection, cleaning up deleted files, and making sure data was still properly replicated after failures, right?
Exactly, things like re-replication, rebalancing. However, the big trade-off with relying solely on in-memory storage is, of course, the risk of losing all that state if the master server were to crash.
Right, RAM is volatile, so how do they make it durable?
That's where the operation log comes in. While the master keeps the current state in memory for speed, it also persistently records every single change to the critical metadata, the namespace, and the file-to-chunk mappings in an operation log.
Like a journal.
Exactly like a journal. This log is written sequentially to the master's local hard drive. And crucially, this log is also replicated synchronously to other machines for safety before the operation is confirmed to the client.
So the log acts as a permanent, reliable record of all the important changes to the file system structure if the master crashes.
It can recover its entire state by first loading the most recent checkpoint, and then simply replaying the sequence of operations recorded in the log since that checkpoint.
Ah, checkpointing, so they didn't have to replay the entire log from the beginning of time.
Correct. To make restarting much faster, and to keep the log from growing indefinitely large, GFS periodically saved a compact snapshot of its current in-memory state to disk. This checkpoint, in a B-tree-like structure, was also stored persistently, both locally and on remote replica machines.
So restart involves load the latest checkpoint, then replay the relatively small portion of the log written since that checkpoint.
Exactly. It's a standard technique, but essential here. It balanced the speed of in-memory operations with the need for durability and reasonably fast recovery.
That's smart. Now, what about the third type of metadata, the locations of all those chunk replicas? You mentioned the master keeps that in memory too, but you said earlier it doesn't keep a persistent record of that, unlike the namespace and mappings. Why the difference?
Yeah, that's a really interesting point. Initially, they apparently did try to maintain a persistent record of where each chunk replica was located, but they found it was actually simpler and more reliable in their highly dynamic environment to not persist this information in the master's log or checkpoints.
Simpler not to save it. How does that work?
Instead, the master just asks the chunk servers themselves about the chunks they're storing when the master starts up. And then it keeps this information updated through regular heartbeat messages that each chunk server sends periodically to the master.
So the chunk servers basically report their inventory to the master.
Exactly. This approach avoided the constant challenge and complexity of trying to keep the master's persistent records perfectly synchronized with the reality of servers joining the cluster, leaving, failing, restarting. All very common events in a large distributed system.
The chunk server is the ultimate source of truth for what's on its own disks.
Precisely. It simplified the master's recovery and avoided potential inconsistencies if the master's persistent state got out of sync with the chunk servers during failures.
That makes a lot of sense. Avoid complex synchronization if you can just ask the source. Now, GFS has this relaxed consistency model you mentioned earlier. What does that actually mean for the applications using it? It still sounds a bit unsettling.
Yeah, relaxed can sound a bit scary in the context of data.
Oh.
Unlike some file systems that guarantee strong consistency, where every client sees the exact same data at the exact same time, Always GFS offers a slightly more flexible or perhaps pragmatic set of guarantees tailored for their specific distributed applications.
Yeah.
So changes to the file system's structure, things like creating files, deleting files, renaming those, are atomic. They happen completely or not at all, managed centrally by the master using locks, and everyone sees the same result eventually.
That sounds good. But what about the data within the files?
Right. When it comes to the data within the files, the state of a file region after a data modification, a write or an append, depends on whether the operation was successful, whether it failed, or whether multiple modifications were happening concurrently to the same region.
Okay, break that down. If one application successfully writes to a part of a file and no one else is messing with that same part at the same time,
Then that region of the file is considered consistent and also defined. Everyone who reads it later will see exactly what was written by that successful, non-concurrent write. That's the straightforward case.
makes sense. What about concurrent writes?
Okay, now if you have several applications successfully writing to the same region of a file at roughly the same time, GFS guarantees that the region will end up consistent, meaning all replicas will eventually have the identical sequence of bytes, but the content itself is considered undefined. Undefined, meaning it might be a scrambled mix of fragments for the different concurrent writes. The writes happened atomically, but the interleaving isn't predictable. All clients will see the same final mixed-up data, but it might not be what any single writer intended for the whole region.
Okay, consistent but potentially garbled. And if a write operation fails?
Right, if a write fails for some reason, maybe the client crashes mid-write, or there's a network issue communicating with the replicas, the affected region of the file could end up in an inconsistent state.
Inconsistent meaning different clients might see different data if they read that region. Or even the same client reading twice might see different things.
Potentially, yes. Or a replica might contain data that the client never even successfully wrote. It's the failure case. The paper basically says applications should assume failed mutations leave the region inconsistent.
Wow, that sounds like it could lead to chaos. How do applications actually work reliably with these potentially undefined or inconsistent states? They can't just ignore it, can they?
No, they can't ignore it. Their applications were specifically designed to handle this relaxed model. The paper highlights common techniques they used.
Like what?
Well, primarily relying on appending data rather than overwriting existing data. Appends are generally easier to reason about, using application-level checkpointing to mark known good points in their data streams. And, very importantly, writing self-validating, self-describing
So
records.
self-validating records.
Yeah, records that include things like checksums within the record itself, maybe unique identifiers. These allow the reading application to verify the integrity of the data it receives. It can detect and discard any extra padding GFS might have added, or maybe handle duplicate entries that can occur, especially with that atomic record append operation we keep mentioning.
Right, the atomic record append. That was another key feature designed specifically for their workload, to handle concurrent additions. How did it ensure that even with many applications writing at once, data wasn't lost or corrupted, despite this relaxed model?
So atomic record append is a special type of write. The key difference from a normal write is that the client only provides the data it wants to add. It doesn't specify the offset, the exact location in the file. GFS itself chooses the offset, guaranteeing to append it atomically at least once.
At least once.
Yes, it guarantees that each client's data record will be added to the file as a complete, indivisible unit somewhere after the previous data, even if there are multiple clients appending concurrently, and even if there are failures and retries.
So you won't get partial records written.
Correct. You won't get half a record from one client interleaved with half a record from another. The append itself is atomic. This was absolutely essential for things like distributed logging systems or merging results, where you can't afford to lose entire entries, and where the exact sequential order of concurrent entries isn't always critical, as long as they all get recorded eventually.
So even if there are network hiccups or retries that might cause the same record to be appended more than once?
Which the paper acknowledges can happen.
The fundamental guarantee is that the intended data is written atomically at least once. The application layer then needs to be prepared to potentially handle duplicates, maybe using those unique IDs within the records.
Exactly. The application needs to be tolerant of potential padding between records or occasional duplicates, but it can rely on the fact that successfully appended records are there in their entirety.
Okay, now let's talk about some of the key interactions within the system to make all this happen. You mentioned leases earlier. What role did they play in keeping things consistent, especially when you have multiple copies, multiple replicas of the same data chunk?
Right. Leases are absolutely crucial for managing writes, or mutations as the paper calls them. The master uses leases to maintain a consistent order for any modifications made to a chunk that has multiple replicas.
How does that work?
The master grants a time-limited lease to one of the chunk servers holding a replica, designating it as the primary replica for that specific chunk for the duration of the lease.
Okay, one replica gets to be the boss for a while.
Kind of, yeah. This primary replica is then responsible for deciding the serial order in which all changes, writes, or record appends are applied to that chunk. All the other replicas for that chunk, the secondaries, simply follow the order dictated by the primary.
So the primary acts like a traffic cop for writes to a specific chunk, ensuring everyone applies the changes in the same sequence. That's how they achieve consistency across replicas despite concurrency.
Exactly. It imposes a single total order on mutations for that chunk while the lease is valid.
So walk me through the process. A client wants to write some data.
Okay. First, the client asks the master, who holds the lease for this chunk and where are the secondary replicas? Unquote. The master replies, potentially granting a lease to one replica if none exists, or the old one expired. Let's say replica A is the primary, B and C are secondaries.
Got it. Primary A, secondaries B and C.
The client then pushes the data it wants to write, just the bytes, to all the replicas A, B, and C, often in parallel or pipelined.
So the data goes everywhere first.
Yeah, get the data staged. Once all replicas acknowledge they have received the data, the client sends the actual write request only to the primary, replica A.
Okay, just the instruction goes to the primary.
Right. The primary receives this request, assigns the next sequential serial number to this mutation, say serial number 123, applies mutation to its own local copy of the chunk at the correct offset, and then forwards the same write request, including serial number 123, to the secondary replicas B and C.
And the secondaries.
The secondaries receive the request from the primary. They apply the mutation in the same serial number order. So they wait for 122 if they haven't seen it yet, then apply 123. Once they've applied it, they reply back to the primary saying, okay, done.
And once the primary gets acknowledgments from all secondaries.
It then finally replies back to the client saying success.
Right.
Or if there was an error anywhere along the way, it reports an error, and the region might be left inconsistent.
Wow, that's quite a protocol. And these leases aren't held forever, right? They have a limited lifespan.
Correct. Leases have an initial timeout period, the paper says typically 60 seconds. But the primary can ask the master for an extension if it's still handling mutations for that chunk. These extensions are often just piggybacked onto the regular heartbeat messages that chunk servers are constantly sending to the master anyway, so it's quite efficient.
Reduces the overhead of constantly renegotiating leases if a chunk is active. What about the actual flow of the data being written? Did that also go serially through the primary replica? That sounds like it could create another bottleneck, especially for large writes.
That's a great question. And interestingly, no. To make the most efficient use of the network bandwidth, GFS cleverly decouples the flow of the actual data from the flow of the control messages, like the write request and acknowledgments.
Decouple data and control flow. How did that work?
While the control messages follow that client primary secondaries path we just described, the client pushes the potentially large bulk data itself directly to all the replicas, often in a pipeline fashion, along a chain of chunk servers.
That's declined.
Yeah, the system tries to pick an efficient path. The client might send the data to the closest chunk server, network-wise. That chunk server starts receiving it and simultaneously starts forwarding it to the next closest chunk server in the chain that hasn't received it yet, and so on, like a bucket brigade.
So the data might hop from one chunk server to another on its way to all the copies, using the chunk server's network links efficiently.
Precisely. It takes advantage of the aggregate bandwidth of the chunk servers and tries to avoid making the client's network link the sole bottleneck for pushing data to multiple replicas. It chooses the chain to minimize latency by considering the network topology.
Very smart network optimization. Let's revisit that atomic record append quickly. You mentioned GFS chose the offset. How did it handle situations where adding a record might make a chunk exceed its maximum 64 millibit size? It can't just write past the boundary, can it?
No, it can't. If the primary replica, when processing an atomic record append request, determined that appending the new record would cause the chunk to grow beyond the 64 millibit limit,
What then?
it wouldn't try to append partially. Instead, it would first pad the current chunk out to the full 64 millibit boundary with some kind of padding data. Then it would instruct the secondary replicas to do the same padding. And finally, it would reply back to the client telling it to retry the append operation, but directed at the next chunk in the file.
So the client gets told, chunk full, try the next one.
Essentially, yes.
Yeah.
And the client library would handle this retry automatically.
Yeah.
There was also a rule mentioned that a single record append couldn't be larger than, I think, 1/4 of the maximum chunk size, so 16 OPA.
Why that limit?
Probably to prevent a pathologically large record from always failing, because it could never fit even in an empty chunk if it was, say, 70 millibay. And also to ensure that if a chunk needed padding, the amount of wasted space wasn't excessive, and there would likely be space in the next chunk for the retry.
Got it. And even with these potential retries and the fact that GFS was choosing the offset, the at least once guarantee of atomicity for the record itself still held.
Yes. For the append operation to be considered successful by the client, the data record had to have been successfully written atomically at the same GFS-chosen offset on the primary and all secondary replicas of some chunk. This ensured that the data was recorded as a complete unit somewhere. Subsequent appends would then be directed by GFS to a later offset in the same chunk, if there was space, or, after padding and retry, to the beginning of the next chunk in the file.
It's complex, but you can see how it provides a useful primitive for their specific needs. Now, GFS also had this really interesting snapshot operation. How did they manage to create near instantaneous copies of potentially huge files or even entire directory structures? It sounds like some kind of wizardry.
It's definitely clever. It relies on a well-known technique called copy on write, or
Okay,
CLW.
bumpy on right?
Yeah. When the master receives a request to create a snapshot of, say, file A to create file B,
Hmm.
the first thing the master does is revoke any active write leases on all the chunks that belong to the source file A. This is important because it ensures that any subsequent writes to those chunks will require contacting the master again.
Okay, pause any ongoing writes.
Right. Then, the master records the snapshot operation in its operation log for durability, and then it essentially just duplicates the metadata for file A in memory. So now, file B's metadata points to the exact same list of chunk IDs as file A.
So at the moment the snapshot command completes, the data itself hasn't actually been copied at all. It's just two file names pointing to the same physical data chunks.
Not at all. That's the magic. It's almost instantaneous because it's purely a metadata operation on the master. The actual copying of any data is deferred until it's absolutely necessary.
When does it become necessary?
It happens only when a client later tries to write to one of the chunks that is now shared between the original file A and the snapshot B. The client asks the master for a lease to write to that chunk. The master looks at its metadata, sees that this chunk, say chunk X, is referenced by both file A and file B. Its reference count is greater than 1.
Huh.
At that point, before granting the right lease, the master tells one or all of the chunk servers holding chunk X, hey, make a new copy of chunk X, let's call it chunk Y, right there on your own local disk.
So the copy happens locally on the chunk server holding the original.
Yes. Crucially, this avoids any expensive network transfer for the copy itself. Once the chunk server confirms it has created the new copy, chunk Y, the master updates the metadata for whichever file was being written to, say file A, to point to this new chunk Y instead of the original chunk X. File B continues to point to the original unchanged chunk X.
And then the client gets the lease.
Then the master grants the client the right lease, but for the new chunk Y. The client can then write to chunk Y normally, completely unaware that this copy-on-write mechanism just happened behind the scenes.
That is very efficient. Minimal disruption, minimal data movement until absolutely needed. Now, the master clearly had a tremendous amount of responsibility. Managing the namespace, handling replication, overseeing garbage collection, snapshots, leases. How did it juggle all these different tasks concurrently without getting bogged down or having operations block each other for too long?
That's a key challenge in any centralized controller. Many of these master operations, like creating a snapshot of a large directory or deciding to re-replicate a whole bunch of chunks after a failure, could potentially take a significant amount of time to complete, especially the logging part.
Right. You don't want one slow operation holding everything else up.
Exactly. To prevent one long-running operation from blocking others, the master was designed to allow multiple operations to be active concurrently. It used a system of fine-grained read-write locks on different parts of the file system's namespace, essentially, the directory and file structure in memory.
Read-write locks,
Meaning operations that only need to read metadata, like just looking up a file path, could happen concurrently with many other reads. But operations that needed to modify the structure, like creating a file, deleting a directory, or taking a snapshot, would acquire write locks, which would prevent other conflicting modifications in the same part of the namespace while still allowing concurrent reads elsewhere.
So different tasks could proceed in parallel as long as they weren't trying to modify the exact same file or directory simultaneously.
Essentially, yes. Their locking mechanism was quite granular, operating on individual namespace nodes, which represented path components. For example, creating a file dir1 subdir2 file3.txt would typically require read locks on bone dir1 and dir1 subdir2 to prevent them from being deleted or renamed during the operation, and then a write lock specifically on the name file3.txt within the subdir2 node.
Okay, that allows a lot of concurrency.
Yes, it allows concurrent file creations in different directories or even within the same directory on different file names. But it prevents, say, dir1 subdir2 from being deleted or snapshotted while file3.txt is being created within it. They also use standard techniques like always acquiring locks in a consistent global order, e.g. top-down in the namespace tree, to prevent deadlock situations where two operations get stuck waiting for each other to release locks.
Smart. Now, what about ensuring that the data itself, those replicas, were spread out effectively across all those numerous chunk servers? How did the master decide where to place new replicas of a chunk, whether for a new file or for re-replication?
The replica placement policy had two main, sometimes competing objectives. First, maximize the reliability and availability of the data. That means making sure it could survive failures, even entire racks of servers going down simultaneously. Second, optimize the overall network bandwidth utilization, both for writes and especially for reads, by trying to spread replicas across different locations so read traffic could be served from nearby copies.
So how did it balance those goals?
To achieve this, the master considered several factors when deciding where to place a new replica of a chunk. It preferred chunk servers that had below-average disk space utilization, trying to balance storage load across the cluster.
Makes sense.
It would also limit the number of replicas that were recently created on any single chunk server to avoid overwhelming that server with a sudden burst of write traffic or cloning activity.
Spread out the creation load, too.
Right. And crucially for reliability, it aimed to distribute the replicas of the same chunk across different physical machine racks within their data centers. The goal was usually to have at least one replica on a different rack from the others.
So that the data would still be accessible even if an entire rack experienced a power outage or network switch failure.
Exactly. Surviving correlated failures like rack failures was a key design goal.
That makes perfect sense. And what about when a chunk lost one of its replicas because a server went offline or a disk died? How did GFS handle the process of re-replication to get back to the desired number of copies?
The master was constantly monitoring the replication levels of all chunks in the system, primarily using those heartbeat messages from the chunk servers. As soon as it detected that the number of available, healthy replicas for a particular chunk had fallen below the configured target, usually 3,
It flagged it.
it flagged it and prioritized that chunk for re-replication. The priority wasn't just random. It was based on several factors, like how far the current replica count was from the target. A chunk with only one replica was higher priority than one with two, whether the chunk belonged to a file that was currently being actively used by clients, and whether the lack of replicas was potentially blocking any client operations that required a certain number of copies.
So it tried to fix the most critical problems first.
Right. Once a chunk was selected, the master would choose an existing healthy replica as a source and then select a suitable destination chunk server for the new copy, again considering factors like disk space, current cloning activity on the target server, and crucially, placing the new replica to improve rack diversity if possible. It would then instruct the source chunk server to clone the chunk data directly to the destination chunk server.
Okay. And what happened when files were deleted by a user or an application? Did GFS immediately reclaim that storage space, scrubbing the bits off the disk?
No, interestingly, they implemented a lazy approach to garbage collection, not immediate deletion.
Lazy garbage collection.
Yeah. When a file was deleted by a client operation, the master simply recorded the deletion in its operation log, and then effectively just renamed the file in its internal namespace to a special hidden name that included a timestamp of when it was deleted. The file wasn't truly gone yet.
So it's like moving it to a hidden trash folder?
Kind of, yeah. Then, during the master's regular background scans of the entire file system namespace, it would identify these hidden time-stamped files. If a file had been in that hidden state for longer than a configurable grace period, the paper says the default was 3 days, then the master would finally remove its metadata entirely from memory.
And only at that point were the links to the underlying data chunks actually severed.
Exactly. Only when the file's metadata was truly gone did the chunks it referenced become orphaned. Then, in separate background scans of the chunk namespace or via the chunk server's heartbeat reports, the master would identify these orphaned chunks, chunks no longer referenced by any file, and instruct the chunk servers to physically delete their replicas.
Wow, that's quite a delayed process. 3 days is a long time in computer terms. What were the advantages of taking this more relaxed, lazy approach to deleting files?
There were several significant benefits, especially in a large, complex distributed system. First, it significantly simplified the overall system design. Immediate, synchronous deletion across multiple replicas in the face of potential failures and network issues is actually quite tricky to get right.
Okay, simplicity is good.
Second, it provided a more robust way to eventually clean up orphan data chunks, even if the initial deletion messages or state updates got lost or delayed due to failures. The background scans would eventually catch everything. Third, it helped to amortize the cost of storage reclamation, spreading out the workload into background activity rather than incurring the cost immediately upon every single delete operation.
Less impact on foreground operations.
Right. And perhaps most surprisingly useful, it offered a built-in safety net against accidental deletions. Since the file wasn't truly gone for that grace period, administrators often had a window to undelete a file relatively easily by just renaming it back from its hidden state.
Ah, the accidental RRF protection.
Kind of. The main downside, of course, was the delay in making that storage space available for reuse. If you deleted a huge file, you might not get a disk space back for 3 days.
Could they speed it up if needed?
Yes, they apparently added mechanisms to allow administrators to explicitly trigger the deletion again, which would force an earlier reclamation. And they could also configure different garbage collection policies, perhaps shorter grace periods, for specific parts of the namespace if needed.
Flexible. Now, one more thing about replicas. How did GFS keep track of which chunk replicas were actually up to date? Especially if a chunk server had been offline for a while during writes, missed some updates, and then came back online. It might have a stale version of the chunk.
That's another critical piece, stale replica detection. They use chunk version numbers for this.
Version numbers for each chunk.
Yes. The master maintained a version number for every single chunk in the file system, stored as part of its in-memory metadata. Whenever the master granted a new lease on a chunk, which typically happens just before a write or record append,
It bumps the version.
it increments the version number for that chunk. It then informs the primary and secondary replicas involved in that mutation about the new, higher version number. They store this version number along with the chunk data.
Okay, so how does this detect staleness?
If a chunk server was down or unreachable when a mutation happened and the version number was incremented, its local copy of the chunk wouldn't get the updated version number. When that chunk server eventually restarted and reconnected to the master, during the initial handshake or via subsequent heartbeats, it would report the list of chunks it holds and their version numbers to the master.
And the master compares.
The master compares the version number reported by the chunk server with the current authoritative version number it has stored in its memory for that chunk. If the chunk server reports a lower version number, the master knows immediately that this replica is stale. It missed one or more mutations.
And what does it do with a stale replica?
It effectively treats it as non-existent. It won't direct any client reads to that stale replica, and it will typically trigger re-replication soon, cloning a fresh, up-to-date copy from a good replica to replace the stale one. The stale replica itself would eventually be garbage collected during the master's background scans.
And the master uses these version numbers elsewhere too.
Yes, the master includes the current chunk version number when it tells the client where chunk replicas are located. The client then includes this version number when it contacts a chunk server, ensuring it doesn't accidentally read from a replica that the master already knows is stale but maybe hasn't been garbage collected yet. It's a belt and suspenders approach to ensuring clients read current data.
Very thorough. Given the sheer scale and the number of components involved in GFS, ensuring fault tolerance must have been just a massive undertaking. Beyond just replicating the data chunks in the master log, what other mechanisms did they employ to achieve high availability and protect the actual integrity of the data?
Yeah, fault tolerance was woven into the fabric. Fast recovery was another critical design principle we touched on briefly. Both the master server and the individual chunk servers were engineered to be able to restore their internal state and restart very quickly. The paper says within seconds after any kind of termination, whether it was a planned shutdown or an unexpected crash.
Seconds. That's impressive.
It minimized the overall downtime significantly. Clients, using the GFS library, were designed to handle these temporary outages gracefully. They'd experience a brief delay, maybe get an error, but then automatically reconnect to the restarted server and transparently retry their pending requests.
That sounds essential for maintaining continuous service, or something close to it. And for ensuring the data itself wasn't corrupted, maybe due to disk errors or network glitches, they couldn't just rely on having multiple copies, could they? What if the data got subtly corrupted on disk and then replicated?
Exactly. Replication helps with availability after failures, but it doesn't inherently protect against silent data corruption. That's where checksumming came into play, and GFS was quite rigorous about it.
Checksumming the data chunks.
Yes, each chunk server independently verified the integrity of the data it stored. It divided each 64 millibit chunk into smaller, contiguous 64 KE blocks. For each of these 64 KB blocks, it calculated and stored a 32-bit checksum.
So lots of little checksums for each big chunk. Where were they stored?
These checksums were kept both in the chunk server's memory for quick lookups and also stored persistently, typically with logging, separate from the actual user data blocks.
Okay, and how were they used?
Whenever a chunk server received a read request from a client for a certain range of data within a chunk, before returning that data, it would first locate the relevant 64 KBL blocks covering that range. For each block, It would recalculate the checksum from the data it was about to send and compare it to the previously stored checksum for that block.
And if they didn't match?
If there was a mismatch, bingo. It indicated that the data on disk had somehow become corrupted since it was last written or last verified. In that case, the chunk server would not send the corrupted data to the reader. Instead, it would return an error, both to the requesting client and likely also reporting it back to the master.
And then the system would recover.
Yes, the client library, upon getting the error, would typically ask the master for other replica locations and retry the read from a different chunk server. Simultaneously, the master, having been notified of the corruption or inferring it from failed reads, would initiate re-replication, cloning the data from a known good replica to create a new, healthy copy, eventually replacing the one with the corrupted block. The faulty replica would then be deleted.
So each chunk server was actively policing the integrity of its own data at a very granular 64 KB level. That's a fantastic way to catch silent data corruption that might otherwise go unnoticed.
Absolutely critical at their scale. And they claimed the performance impact of this checksumming on reads was minimal.
Why minimal? Seems like extra work.
Well, first, most reads were large and sequential, often spanning many 64 KB blocks, so the overhead was amortized. Second, the checksum lookups were just in memory, very fast. Third, the actual checksum calculation could often be overlapped with the I/O operations reading the data from disk. For abundance, the checksum calculation was also highly optimized, just incrementally updating based on the new data. Overwrites were a bit more involved, requiring reading and verifying the block before rewriting it.
And they even checked inactive data.
Yes, they mentioned having background processes running on the chunk servers to periodically scan and verify the checksums of chunks that hadn't been accessed recently, inactive chunks, just to proactively catch any latent corruption, sometimes called bit rot, that might have occurred silently over time on the disk.
Very comprehensive. Finally, in a system as complex and distributed as GFS, with so many moving parts, diagnosing problems when they inevitably occurred, and understanding performance characteristics must have been a significant challenge in itself. What kind of diagnostic tools did they build into the system?
You're right. Diagnosis is key. The paper emphasizes that extensive and detailed diagnostic logging proved to be absolutely invaluable.
Logging everything.
Pretty much. GFS servers were designed to record significant system events like chunk servers joining or leaving, master failovers, etc., and also detailed information about all the remote procedure calls, RPCs, the requests and responses exchanged between different components like the master, chunk servers, and clients.
But not the actual file data itself in the logs,
Oh
presumably.
no, definitely not the file data. That would be way too voluminous and unnecessary. But logging the metadata, the operations, the parameters, the success failure status, and timestamps was crucial.
And these logs were persistent.
Yes, written to local files on each server. The paper notes that these logs could technically be deleted without affecting the correctness of the running system, but they were generally kept for as long as disk space allowed because they were so useful for debugging.
How did they use them?
By carefully examining and correlating these logs across multiple machines involved in a particular interaction, the engineers could reconstruct the sequence of events leading up to a problem, making it possible to diagnose even complex intermittent issues that are notoriously hard to track down in distributed systems. These logs also provided excellent raw data for analyzing system performance, identifying bottlenecks, and understanding workload patterns.
Did all this logging slow things down?
They say the performance impact was minimal. Log entries were typically written sequentially to disk, which is relatively efficient. And the logging process itself was generally asynchronous, meaning the main server thread wouldn't block waiting for the log write to complete. Plus, recent log events were often kept buffered in memory, making them easily accessible for real-time online monitoring and immediate troubleshooting without even needing to parse the disk files.
Fascinating. It really sounds like building GFS involved this constant process of making incredibly smart design trade-offs, all driven by Google's unique challenges at the time, the massive scale, the specific workloads, and the realities of operating on relatively inexpensive, failure-prone commodity hardware. What are the key insights or lessons we should really take away from this deep dive into GFS?
I think the biggest takeaway is that the Google file system was truly groundbreaking because it dared to challenge the conventional wisdom of file system design prevalent at the time. It consciously prioritized practical considerations like dealing with frequent component failures and handling massive aggregate throughput over striving for the absolute strongest consistency guarantees or the lowest possible latency for every single operation.
That fundamental shift in assumptions really drove everything else.
It really did. It led directly to that whole set of innovative, sometimes counterintuitive design choices we've discussed. How it managed scale, how it ensured reliability through replication and fast recovery, how it handled data access patterns with large chunks and in-focused operations. Another key insight is just how beneficial that co-design approach was, tailoring the file system with their specific applications like MapReduce in mind. That allowed for optimizations like the relaxed consistency model and the atomic record append that wouldn't necessarily be suitable for all general-purpose use cases, but were absolutely perfect for Google's internal needs back then.
Yeah, and it's really striking how effective some of their core decisions turned out to be, things that might seem non-obvious at first glance, like embracing the inevitability of failure as the norm, and building replication, checksumming, and fast recovery right into the core, using that surprisingly large 64 millibit chunk size, which had so many benefits for reducing metadata overhead and client master chatter, and the controversial, maybe, but ultimately effective central role of that single master for coordination and global optimization, despite the immense scale of the system.
Absolutely. These choices weren't always the standard ones you'd find in textbooks, but they proved to be incredibly powerful and pragmatic in practice for the problem they were solving. And, this deep dive has really given you, the listener, a foundational understanding of critical piece of infrastructure that, in many ways, laid the groundwork for much of the cloud computing and big data systems we rely on today.
It really did set a pattern. So here's a final thought for you to consider. How have these core design principles of GFS, things like prioritizing resilience and high throughput in the face of massive scale and frequent failures, sometimes at the expense of strict consistency or low latency, how have those ideas influenced the architecture of other large-scale distributed systems that have emerged since then? Think about systems like Hadoop HDFS, or various NoSQL databases, or modern cloud object storage. What are the trade-offs inherent in this GFS-like approach, and how are they still being debated and refined today in the world of cloud storage and big data infrastructure?
That's a great question to ponder. The echoes of GFS are definitely still felt today.
We really encourage you to continue exploring the fascinating evolution of distributed file systems and cloud technologies. Thanks for joining us for this deep dive.